Welcome back, everybody. Today we're going to be looking at lesson 10-5. 10-5 is over tangents. This is not the tangent that we talked about when we talked about right triangles. This is a totally different type of tangent that comes with circles. So let's go ahead and go to our notebook and get started. Okay. Around here. All right, this is lesson 10-5. And it is on tangents. And again, this is not a tangent like a trigonometric property tangent. This is talking about circles. So let's talk about what is a tangent. Let's just talk about defining a tangent first of all. So a tangent is a line that intersects a circle in exactly one point. That point, so the point that it actually touches, is called the point of tangency. So tangent is a vocabulary term, and point of tangency is a vocabulary term. So if we have two circles that have a tangent that intersects both, is called a common tangent. So common tangent is also a vocabulary term. So let's take a look at common tangents. So we're going to put this in here. Oops. There we go. I bumped my iPad, and it disconnected for just a second. So it says copy each figure and draw the common tangent. So a common tangent would be a line, a ray, or a segment that touches two circles. So right there and right there is our point of tangency. We also have one that's going to go this direction. And right there and there are points of tangency. And so this one has two common tangents. If they are separate from each other, that's totally okay. You're still going to have some common tangents. So you've got one going this direction. You've also got one going this direction. But then you also have one that's going to go this way. And we're going to pretend that those touch. I didn't draw the line very well. And then you're also going to have one that goes this way. So this one has four common tangents when they're separate from each other. So this guy over here, again, has this one and this one. But it also has one right here where they touch. So where the two circles themselves come together, there is an additional tangent. So, and then this one right here, the only common tangent it's going to have is where the two circles touch together. And then you have one tangent that touches with them. So those are all common tangents. Okay, so the next part is a theorem that says a line is tangent to a circle if and only if, so therefore we know that it's a biconditional, so it works both ways, if and only if it is perpendicular to a radius. And so what I mean by that is if you have a tangent, the only way that this is tangent is if it is perpendicular to a radius. If it's not perpendicular to a radius, then it's not considered a tangent. It will always be perpendicular to a radius. And so when it comes to perpendicular lines, then we know that it can fall right into right triangles and right angles. And so therefore we have some right triangle things that apply when it comes to perpendicular bisectors. So the next set says if JL is a radius of J, determine whether KL is tangent to circle J and justify your answer. Well, we know that if this is tangent, so if KL is tangent to the radius, then we know that this would have to be a right triangle. If it's not a right triangle, then it's not a tangent. And so this is just simple Pythagorean theorem, but you have to be careful because this part right here is that 9. See, it wouldn't make any sense if this whole thing is 9 because the length of the side would have to be, the hypotenuse has to be the longest. So if this radius is 8, then this is also 8. So we have to be a little careful. So this is a 8 and 15 and 17. So 8 squared plus 15 squared should equal 17 squared if it is a tangent. So 64 plus 225. And does that equal 289? Can it be 9 and 8 and 2? And it does. So therefore, yes, this is a tangent. And it says justify your answer. So because Pythagorean theorem works. So there's our justification. Pythagorean theorem works, so we know it's a right triangle. So again, determine whether GH is tangent to F. Again, we're just going to do Pythagorean theorem. So we have an 8 and we have a 6. And so if we know that's 12, then we know this also has to be 6. And so that's 18. Well, we know that that's not right because if we have a 6 and an 8, this would have to be a 10 to be a 3, 4, 5 triangle. So we know that this cannot be. So this is not tangent because the hypotenuse would have to be 10, not 18. So the triangle is obtuse, not right. So there's a justification. Okay, and so that is that for that section. So the next part of this is just finding missing parts. Let's see. So finding missing parts of circles, basically using that same idea. The 1, 2, and 3 would be the next part. So again, if we know that something is tangent, we know it makes a right angle, thus we are making right triangles. And so we can use Pythagorean theorem. So I'm not going to do all of these in the video. You guys can do them on your own for extra practice as we're going along. So JH is tangent to circle G. So therefore we know that that has to be a right angle. Find the value of X. So we're just going to use Pythagorean theorem. So we know that X squared plus 12 squared is going to equal the entire hypotenuse. So the entire hypotenuse would be X plus 8. So X plus 8. You're going to find that these are probably going to have some quadratic type formulas in them. But what's really nice is a lot of times they do cancel themselves out. So this would be X squared plus 16X plus 64. So notice how nice those go away. We can subtract 64 from this side and we end up with 16x equals 80. And then divide 16 to both sides. Whoa. Would be 80 over 16. Oops. Which gives us 5. So x equals 5. So, oh, that problem is exactly the same. That's interesting. And so this one, a lot of times they're not going to give you. So if we know the radius is x, we know that guy also has to be x. And so then again, you just use Pythagorean theorem to figure out what the problem is. So our next theorem that we're going to be looking at says that if two segments from the exterior of a circle, so if two segments from the exterior of a circle are both tangent to the circle, then they are congruent. So what I mean by that is if you have a circle and you have a tangent this way and you have a tangent this way, eventually those two tangents will meet. That's a terrible, terrible picture, but you guys get the point. Then therefore, this is congruent to this. So anytime you see this happen, these two are going to be congruent to each other. This is really interesting because from a point of perspective, so if you're looking at a telescope somewhere at, say, a different planet, you would know that the top of the planet through your telescope is going to be the exact same distance as the bottom of your planet. And then if you know that, you can draw triangles and you can use a lot of trigonometry to figure out the distance of planets from a point of perspective. So this is actually very useful, especially in astronomy. So let's look at some examples of this. And I'm going to let you guys do several of these. I'm only going to do one of them here in the video, and then you guys can do the rest later. So if A, B, and C, D are tangent to circle D, so we know this guy is tangent to this guy, find the value of x. So we're just simply saying that if this is congruent to this, because we know they're both tangent, then we can just write a quick equation. 2x minus 5 is equal to x plus 15. And then we're just going to solve for x by subtracting and adding 5. And we can find out that x equals 20. So pretty easy, just asking for x, make sure that it either, if it's asking for a specific side length or whether it's asking for x, pay attention to what it's actually asking for. Okay, so the next part we've kind of already talked about a little bit, and it is inscribed and circumscribed polygons. And remember, we said that an inscribed polygon would be a polygon that is inside of a circle. So if we have a circle and that polygon touches, its vertices touch the circle in all locations, in all vertices, that is inscribed. And if the polygon is outside of a circle, but it touches in multiple locations, yeah, this is not going to be a good one, but you get the point. Then that would be a circumscribed polygon. So there are some examples of that. In your notes. And what's interesting is if you look at these and you look at this guy, right, or these guys up here, if you were to put another point out here and you drew another set of tangents, all of a sudden you get a circumscribed polygon. And so in a circumscribed polygon, each of these vertices is going to create a tangent. So therefore that is congruent to that. This creates a tangent, so that's going to be congruent to that. And this creates a tangent, so that one's congruent to that one. Doesn't mean they're congruent to each other, but they have to be congruent to the other tangent. So this actually is what is created by circumscribed. In fact, the definition of circumscribed, or not the definition, but how we know they're circumscribed, is a polygon is circumscribed if every side of the polygon is tangent to the circle. So that's basically the definition of circumscribed, is that they're tangent to the circle. So our last set of questions deals with this. So if we have this polygon, it is circumscribed. We know that then each of the vertices is going to be, or each of the sides is going to be tangent to the circle. And we know that the perimeter is 18x. So if this one is 3, we know that this one has to be 3. If this one is 3, we know that this one has to be 3. If this one is x, we know this one has to be x. And if this one is x, we know this one has to be x. So if we're just trying to find the perimeter, we know that x plus 3, that's one side, and 3 plus 3 is one side, which is 6. And x plus 3 is one side. And x plus x is the last side, so 2x. And we know that the perimeter equals 18. And now we just have an equation to solve. So we have 1x, 2x, 3x, 4x, and 9, 12 plus 12 equals 18. And so we subtract 12 from both sides, and we get 4x equals 6. So we know that x equals 3 over 2. And then again, same thing here. If we know this one is 14, we know that that one is 2x. So therefore x has to equal 7. That was easy enough. And then it also asks us to find the perimeter. So if we know this one is 17, then we know this guy over here has to be 17, which means this whole thing is 27. So we know that has to be 10 and that has to be 10. So if we're going to find the perimeter, we know that this is 24. And we know this side is 27. And we know this side was 14 and 17, which is 41. And then we would just add them together to find the perimeter. And so this is the last one. It works the same way as the other ones. So that is all for lesson 10-5. If you have any questions and you want to go through some more problems with me, I'd be more than happy to talk to you about that. Just come and see me. So until next time, we'll see you later.